We've just looked at what the definite integral was and the definition. And so let's just kind of review that really quickly. And then we're going to get into the fundamental theorem of calculus, which will help us find area under the curve or to find definite integrals without having to do these Riemann sums, adding all these rectangles underneath the curve and taking the limit as n goes to infinity. So this will be an easier way to do this. But first, the definite integral, recall from an interval from a to b, we could write it with the integral sign, the a on the bottom, b on the top of f of x dx is a number to which all Riemann sums tend as the number of rectangles approaches infinity and the width of the rectangle tends to 0. And we wrote that as that limit as n goes to infinity. I told you about that symbol. That means that you're just summing all these things from I equals 1 to n of f of c sub I times triangle x sub I, where that triangle x sub I was the base, that width of each rectangle. Where triangle x sub I guess it said it here, is the width of each ith rectangle, and c sub I is the x coordinate of the point where the ith rectangle touches f of x. Okay, so that takes us a long time to actually do. And there's an easier method, which is called the fundamental theorem of calculus. And so this tells us that if our function is continuous in an interval of a, b, then the following is true. If we're looking at this definite integral from a to b of f of x dx, all we have to do is find the antiderivative of this f of x. And once we find that antiderivative, we can plug in our upper bound minus, and then we can plug in our lower bound into that antiderivative. Here, the function of f is the antiderivative of little f. And remember, if we took the derivative of our antiderivative, we got back our original function f, little f, which was our integrand. So let's look at an example of doing that. But actually, before we do that, let's just kind of review. This is kind of a review of what we did when we were looking with indefinite integrals. We had those properties so that we could integrate really easily. The other thing that we have to kind of touch on really quickly, and I had mentioned this when the video wasn't running, was that we were looking at area under the curve. And when we're looking at area under the curve, we have to show that f of x is greater than 0. So we could use this definite integral to find that area under the curve, but f of x has to be greater than or equal to 0. If not, if our curve dips below the x-axis, when we're trying to find those heights, right, and those were at the value of our function, we're getting back a negative number. And so we have to be careful if our graph goes below the x-axis and we're trying to find the area bounded between the curve and the x-axis. If that's the case, we're going to have to find out where it crosses the x-axis and then what interval we're looking at, and take the absolute value of this area. So we would take the absolute value, maybe look at the integral here from, let's say this was a to c of f of x dx. I would have to take the absolute value of that. Oops. I called this c because I was thinking this should be b. Plus, then I would have to take this area of the integral from x equals c to b of f of x dx. We'll look at some of those in a minute, but let's first look at, again, some of those rules or properties that we can use to find the antiderivative. So order of integration. When we're doing integration, our value we've been looking at was that A was less than B. And we were looking at the interval, our x value A comma B. Well, if for some reason you are looking at your integration and A is less than B, but your bound is opposite, because normally this bound up here is where the end bound. So if it's opposite, then we can say, well, this is the same thing as flipping the sign, taking the negative of that answer. If you're looking at an integral, right, from A to A. So if we're doing that, if this is A, well, even if my graph comes up here, and again, I'm thinking about this width here is 0. So my rectangle, that is 0. If we're looking at a constant multiple, so if I have some constant, some number times some function f of x, so for instance, 2x, I can think of 2 as my coefficient, my constant. Remember, we could bring that outside of the integral, and then we could take the integral of our function. So we just kind of ignore it while we're taking the antiderivative, and then we just put it in front. If I have the negative, this is almost the same idea as this. If I can think of this as -1, I could pull the negative out front of my integral. If we had a function that had more than one term, and we were adding and subtracting terms, we could think of each term as a separate function, and we could take the antiderivative of each term. So this is the same idea as the sum and difference here. So the antiderivative, the integral from A to B of f of x plus or minus g of x dx can be rewritten as the integral from A to B of f of x dx plus or minus, depending what sign it was, the integral from A to B of g of x dx. And then the next property is this additive property, which I kind of explained up there when I had the area above the curve and below the curve. Sometimes it's helpful for us to break up an integral. So if we had some integral from A to B, but some of it's underneath the x-axis and some is above the x-axis, and we might want to find the area. Sometimes we're not looking for area, but if we're trying to find the area, we might want to break it up. And so doing that, we can say this integral from A to B of f of x dx plus the integral from B to C of f of x dx is equal to the integral where I started to where I end from A to C. These have to be the same. Okay. And so that's the additive property. So let's actually go back. We had looked at an example and we were looking at it with rectangles and the different endpoints of our rectangle. Let's look at the answer to that using this definite integral. And so we had the bound, we had f of x was equal to, what was it? It was 3x plus 2. And our bounds was from x equals 1 to 3. So to write this as a definite integral, our lower bound goes on the bottom, 1 to 3. Our function here is 3x plus 2, and then we're going to put dx. Okay, so I'm just going to write it here really quickly, what that fundamental theorem of calculus says. So if we have a definite integral from A to B of f of x dx, this is the same thing. Remember that capital letter represented the antiderivative. The antiderivative evaluated at the upper bound minus the antiderivative evaluated at our lower bound. Let's also talk about this one more time. That's just kind of a review really quickly. Remember when we were doing indefinite integrals, and if it was a power like x to the n dx, as long as n didn't equal -1, that was a special case. But if that was, as long as n isn't -1, we added 1 to our exponent, and we divided by that new exponent. We added a value c here. When we're dealing with definite integrals, we don't evaluate that value c. So when we're doing indefinite integrals, we're getting back the antiderivative function. We're getting back a function. When we're doing definite integrals, we're getting back a number. This, it represents multiple functions in here, but this represents a number. Okay, so we don't have to worry about this plus c when we're doing this piece. So let's start. So I'm taking the antiderivative. I can ignore the 3, bring it down at first. And so taking the antiderivative, my exponent is 1, so I'm going to add 1 to my exponent. So 1 plus 1 is 2, and I'm going to divide by that new exponent, 2. Plus, so now taking the antiderivative of 2. So what can I take the derivative of to get back 2? Well, derivative of x, 2x gives me back 2. I'm again not going to write my plus c here. And this is how we denote that we're evaluating this. We remind ourselves that our bounds are 1 to 3. So what we're going to do is we're going to take our value of x. I don't know. So x equals 3 here. And we're going to go in and we're going to plug it in wherever we see an x in this function. So I have 3 parentheses x. So I'm going to go back and put 3 in there, all over 2 plus 2. I see an x there. I'm going to put parentheses and replace it with a 3. So this is my f of b value minus. So you need to be careful here. If this is more than one term that you're taking the antiderivative of, we need parentheses or brackets around this because we're subtracting off this whole value. So we have to do what's inside and then subtract it off. So now let's go in and let's plug in 1 wherever we see an x in this function. So if we do that, we have 3, we see an x, so put parentheses squared all over 2 plus 2, we see an x. We're going to put a parentheses and we're going to go back in there and we're going to put in 1 wherever we had seen an x and just put our parentheses. So now it's just order of operations and simplifying this arithmetic. So we have 3 times 3 squared. Exponents first, 3 squared is 9 times 3. In front is 27 all over 2. Plus 2 times 3, which gives us 6, minus, so let's put our bracket. So 1 squared is 1. And then we have times this 3/2. So 3/2 plus 2. So we can distribute our negative, or we can sum that first, but let's see. Let's distribute. So we have 27/2 plus 6 minus 3/2 minus 2. So I'm going to combine the terms that have common denominators. So 27/2 minus 3/2, that gives me 24/2. And I have a positive 6 minus 2, so that's plus 4. Well, 24/2 is 12, and 12 plus 4 equals 16. So we actually found that was one of our answers. That was one of our answers when we had added the left endpoint result and added the right endpoint result of our rectangles and took the average of those two. We got that answer, and we also got the answer when we looked at the midpoint rule for the height of our rectangle. We also saw that that graph was all above the x-axis between x equals 1 and 2. Okay, so our next example, we're looking at the definite integral from 0 to 4 of 2 times the quantity x to the 1/2 minus x in that quantity dx. And it just tells us to evaluate each of the definite integrals. So we don't have to worry. If it says find the area, we have to worry if it's above or below the x-axis. But this case doesn't say find the area, it just says find the definite integral. So we don't have to worry about it in this case. We can either pull that 2 out in front of the integral, or we can distribute that 2. I would just say let's distribute it, and then let's take the integral. So we have 2x to the 1/2 minus 2x dx. Okay, so taking the antiderivative of 2x to the 1/2. So the 2, we leave it alone. X, we add 1 to our exponent. So 1/2 plus 1. So 1/2 plus 2/2 is 3/2. So last week I said, okay, well, we're going to divide by a fraction. Then just think of it as multiplying by the reciprocal. So we don't have to worry about it later. So if we're dividing by 3/2, that's the same thing as multiplying by the reciprocal, which is 2/3. Minus 2, leave the 2 alone, and now we're going to add 1 to our exponent. So 1 plus 1, that gives me 2, and divide by my new exponent. That's not a fraction, so just put it all over 2. And because we have numbers and it's the definite integral, we're evaluating this from 0 to 4, and we don't have to add that constant. So let's look at this. We have 2 times 2/3. Let's clean it up before we start plugging in numbers. So that gives me 4/3. To me, it's easier if I think of this as a radical, this 3/2 power. So the x to the 3/2 power, the denominator is what root you're taking. So it's the square root of x. We can either put that cubed underneath the radical, or we can actually put it outside. So it's actually easier to deal with smaller number after you take the square root and then cube it. Minus, so notice our 2's cancel here. And we're just left with an x squared. Again, we're evaluating this from 0 to 4. So we plug in the upper bound first, subtract off the lower bound. So we're going to go in here, and wherever we see an x, we're going to plug in 4. So we have 4/3 square root of 4. Then we're going to cube it. Minus, I see an x, so 4 squared. Minus, now we're going to go in there, and wherever we see an x, we're going to go in and plug in 0. And so I get 4/3 times the square root of 0 cubed minus 0 squared. You might have noticed right away that that was going to be 0, and I'm okay if you had just put minus 0 after that, knowing that you knew that was going to sum to 0. But we have 4/3. Square root of 4 is 2, and 2 that we're going to cube. 2 cubed is 8. Minus 4 squared. 4 squared is 16. And then, like we said, this all turns out to be 0. So 4/3 times 8, that gives me 32/3 minus, well, I know I'm going to have to combine these, so we might as well get a common denominator as we're right here when we bring it down. So we can multiply 16 by 3/3. So that gives me 48/3. So 32/3 minus 48/3. This gives us back 16, negative 16/3. So right there, because this is negative answer, To me, I know that at least part of that graph is underneath the x-axis, and the part that is underneath the x-axis, if there is some above, is going to be larger. That area is larger than the one above. But it didn't ask us to find area, so we're okay. Okay, so let's look at an example where we have to actually deal with substitution. So we have some integrand that we don't know how to integrate until we do some substitution. And there's two ways that we can handle that when we're dealing with a definite integral. So let's say you have the integral from 1 to 4. We have -3 in our numerator, all over parentheses 2x plus 1. That's quantity squared in the denominator. And then dx. So this is an integral that is not in the form that I can integrate. So this is where we want to use u substitution. So this is where we went back and we chose something, part of the integrand, to be u, so that when we took the derivative of it, it either canceled out with something in the integrand so we could integrate, or it just made it so that we can integrate. We talked about tricks to look at, or things to look at, which were things inside parentheses, underneath radicals, maybe exponents. So in this case, inside this parentheses, let's choose that to be u. And so that is, u is going to be 2x plus 1. And so then we differentiated both sides. So the derivative of u is 1, but it was with respect to u, so du. Derivative of 2x plus 1, derivative of 2x is 2. Derivative of 1 is 0. And this was with respect to x, dx. So if we went back in here, I'm going to leave the bounds off for a second, -3. And then in here, we have u squared. But we are now in terms of u, not x. So we wanted to rewrite that function dx. And so we could solve for dx here. We could divide both sides by 2, and we would get our dx value is du over 2 times dx, which is du over 2. So I'm going to rewrite this in the form that I know how to take the antiderivative. Remember that we can move up. It's only one term in the denominator. We can move that up into the numerator and rewrite it with a negative exponent. And so this is the same thing as -3/2 of the numerator and our denominator times u to the -2 power du. Okay, so we can, let's do it the way I don't like to do it, which I used to like to do it as a student, but I prefer the other way, and you'll see why in a minute. If we're going to keep our bounds here, and we're not going to change them now, so it's possible to change them now, so that our bounds are in terms of u and not x. Actually, let's do both. And, or we can keep our bounds as x values. If you keep them as x, let's write that in here. X equals 1. X equals 4. X equals 1, or x equals 4. Or we could change the bounds at this point. Our function, we want our function to be in terms of u instead of x. And so we have our bounds where x equals 1. So if x equals 1, let's figure out what u has to be then. So remember, u is 2x plus 1. So when x is 1, my u value I would get back is 2 times 1 plus 1. So 2 times 1 is 2 plus 1 is 3. So I know my lower bound, when x is 1, goes down here as u is 3. And then I can just use the same integrand, -3/2 u to the -2 to u. And so let's look at when x is 4. So when x is 4, if we go back in here, we could figure out what u has to be. So we have 2 times 4 is 8. 8 plus 1 is 9. So our bound here is 9. So we're going to take the antiderivative of this, -3/2 u to the -2 power. So ignore the coefficient, bring it down, -3/2. We're now going to add 1 to our exponent. So -2 plus 1 is -1. Divide by our new exponent, -1. We're looking at this though when x is 1 and x is 4. Where if we do this over here, same thing except different bounds. When I take the antiderivative of this, I get -3/2 u to the -1 over -1. But I'm evaluating these at my values where u is 3 and u is 9. So this case, the second case that I'm doing, I can just go in right now and plug in my 9 and my 3. Maybe I would clean it up a little bit, negatives. So that's +3 over 2. I can make my u to the -1 power positive by bringing it down to the denominator. Now evaluate this from 3 to 9. So we plug in our upper bound first. We have 3/2 or 3 over 2 times our 9 minus our lower bound, which we said was 3. So plugging that in, I have 3 all over 2 times u, which in this case is 3. So I notice I can simplify a little bit. Let me simplify just the first fraction. I see that if I simplify the second fraction, I won't have a common denominator. But if I simplify this first fraction, 3 goes into 9 3 times. So this is the same thing as 1/6 minus 3/6, which is -2/6. Okay, so if you didn't change the bounds, this is where we have to go back and we have to replace what u is in terms of x. So let's do that. And while we're doing it, let's clean it up a little bit. So we have a negative and a negative. So remember that was +3/2. And we're going to put u in the denominator. So if we put u in the denominator, we're going to, instead of writing u, we're going to write what u is, this 2x plus 1. Now we're going to evaluate it from 1 to 4. So when we go in, we're first going to plug in our upper bound. So 2 times 2 times 4 plus 1 minus 3 all over 2, parentheses 2. I see an x, so I'm going to put in 1 plus 1. So now if I simplify, I should get the same result as I got over there. I have 3 all over inside parentheses first. 2 times 4 is 8, plus 1 is 9, and 2 times 9 is 18. Minus 3 all over 2, we'll go inside parentheses first. 2 times 1 is 2, plus 1 is 3. 3 times this 2 out here is 6. Let me reduce this a little bit. So this 3/18 is 1 over 6 minus 3/6, which is -2/6. So we get the same, and I'm surprised I didn't notice this. You need to reduce your fraction. So it's just a -1/3, which is the same thing as -1/3. Same result. I really think it's easier in this case if we had definite integrals to first change your bounds. And then we don't have to worry about going back and doing substitution after we take the antiderivative versus not changing them. Then you have a problem where you might forget that you didn't change them and plug in the values. It just seems a lot longer this first way that I started out doing, where we did not change the bounds first. But it's up to you which method that you would want to use, and I wouldn't knock you down either way. But you'll see me using that second one usually. This next example we're going to look at where we're using the definite integral to find the area between the curve of f of x and the x-axis. And so this is where we have to be careful. We need to see if our function f of x is entirely above the x-axis, and if that's the case, we're fine. Or if it's below, if part of it's below the x-axis. If that's the case, then when we take that, find the area, we have to take the absolute value of the piece below the x-axis. Excuse me. Okay, so let's first look at where does this cross the x-axis. So we can see where that crosses the x-axis by finding out when our y value is 0. So we want to find x-intercepts. And that's where we let y equals 0 and solve for x. So we get 0 is equal to 4x minus 32. It's linear, so I would isolate my x. I would add 32 to both sides, so we get 4x equals 32. Divide both sides by 4. 32 divided by 4 is 8. So now you have to see, is the value where it's crossing the x-axis inside the interval where we're trying to find the bounds of our graph? And it is. And so we need to know, is it below the x-axis from 5 to 8 or below the x-axis from 8 to 10? Well, if you kind of think about this function, you could probably figure it out without graphing it. And this function is increasing, right? My slope is positive. And so if my function is increasing, strictly increasing, that would tell me that it's below the x-axis from 5 to 8, not 8 to 10. And I don't know if that, when I show you my pen or pencil, if that's opposite direction because of the mirror effect. And so when I'm looking at the integral from 5 to 10, f of x dx, and because we want to find the area, we're going to break it down. We're going to look at the integral from 5 to where it crosses the x-axis, which is at 8, of f of x dx. And we need an absolute value around that piece. We want to take the positive of that because we're talking about area. Plus, we're going to then look at the integral starting from 8, and we're going up to 10 of f of x dx. So not too bad, because our f of x is linear. So we're looking at 5 to 8 of 4x minus 32 dx. Absolute value of that plus integral from 8 to 10. Same thing, 4x minus 32 dx. So first, take the antiderivative, and then we'll plug in our bounds, upper bound minus lower bound. So antiderivative of 4x, so add 1 to our exponent, divide by our new exponent. So we get an x squared, divide by 2. So we have 4x squared all over 2, minus antiderivative of a constant is that constant times x, so negative 32x. This is from 5 to 8 absolute value. Plus, we're looking at same answer we got here. It's the same thing we're taking the antiderivative of. You can clean it up. That's going to be 2x squared minus 32x. And that's evaluated from 8 to 10. Okay, upper bound first. So if we plug in our upper bound first, we have 2 all times 8 squared minus 32 times 8. Minus, now plug in 5 wherever you see an x. So it's really 2. So 2 times 5 squared minus 32 times 5. I need a bracket around that whole piece. Plus, now let's go back in and plug in our upper bound 10. And so plugging in our upper bound, we have 2 times 10 squared minus 32 times 10 minus, now plugging in 8, we have minus 2 times 8 squared minus 32 times 8. Okay, and I need absolute values here. So working inside this first parentheses, this is 64. 8 squared is 64 times 2, so that's 128, minus 32 times 8, which is 256. So that 128 minus 256 is negative 128 minus, so inside our bracket, 5 squared is 25 times 2, that is 50, minus 32 times 5, which is 160. This here is going to be negative 110, but I have a minus in front, so this is plus actually 110. Absolute value plus this information here. So 10 squared is 100 plus times 2 is 200, trying to hurry now, minus 320. So here, this is negative 120. Okay. Minus this piece in here. And so this is, we already did that, right? This was negative 128. This one's negative 128. So minus a minus, that's going to give us plus 128. I was a little worried because this has to be a positive number because I know that this was above the x-axis. You notice that that is going to give us a positive number. So negative 128 plus 110, that is a negative 18 inside. Absolute value plus negative 120 plus 128, that is also 18, but positive. So negative 18, absolute value is 18, 18 plus 18. This gives us 36. So depending on what the units is for the area, you have 36 units squared. Okay. So we're going to stop there. So we are a little bit over time already, and then we'll do some more examples of these starting with Thursday's class, and then we'll look at it where we're not just bounding our graph between the function and the x-axis. Maybe it's between two curves. So finding the area between two curves and how we would do that on some interval.